At first, it doesn't look like collapse. The lights are still on. The shelves are not empty yet. The roads still carry traffic. But beneath this surface stability, a measurable shift begins, one that logistics analysts, emergency planners, and supply chain engineers recognize immediately. Grocery panic does not start when food disappears. It starts when flow is interrupted. In 2026, that interruption is no longer theoretical. It is statistical, structural, and already unfolding in specific regions where distribution fragility meets population pressure. The danger is not sudden starvation. It is rapid desynchronization between supply and demand, where even a 48-hour disruption can cascade into localized shortages that amplify human behavior in unpredictable ways. To understand which states are most at risk of running out first, you have to strip away the common misconception that food availability is about production. Modern food systems are not local. They are throughput systems. A typical urban grocery store carries only 3 to 5 days of inventory. That is not a failure. It is an optimization strategy known as just-in-time logistics. Warehouses are not designed to store surplus for emergencies. They are designed to move goods continuously. When transportation slows, when fuel distribution tightens, or when labor shortages reduce delivery frequency, shelves begin to thin, not because food doesn't exist, but because it is no longer arriving at the required rate. The misunderstanding that dominates public perception is the belief that shortages are caused by hoarding alone. Panic buying is not the origin of the problem. It is an accelerant. The real trigger lies deeper in the network. Bottlenecks in trucking routes, refrigeration failures in distribution hubs, or disruptions in port throughput. For example, perishable goods operate under strict temperature-controlled logistics. A delay of even a few hours in a refrigerated chain can render entire shipments unusable, forcing disposal rather than distribution. This invisible loss never appears on shelves, but its absence is felt immediately by downstream retailers. Hidden within this system is a principle known as demand amplification, often referred to as the bullwhip effect. A small increase in consumer demand at the retail level causes progressively larger fluctuations upstream in warehouses and suppliers. When people begin to buy slightly more than usual, whether due to weather alerts, economic uncertainty, or perceived risk, the system overreacts. Orders spike, suppliers misinterpret signals, and inventory allocation becomes uneven. Some regions receive excess shipments, while others experience sudden gaps. The system is not intelligent, it is reactive. And in that reactivity, imbalance grows. Evidence of this vulnerability has already been observed in multiple stress events over the past decade. Short-term disruptions, whether from extreme weather, transportation strikes, or fuel supply constraints, have consistently resulted in empty shelves within 24 to 72 hours in high-density areas. Data from emergency management agencies shows that urban centers with high population-to-store ratios and limited local warehousing capacity are the first to experience visible shortages. These are not hypothetical projections. They are repeatable outcomes documented under controlled stress conditions. The survival implications are not about long-term famine. They are about short-term access failure. When essential items like bread, milk, and water disappear, even temporarily, behavioral thresholds are crossed. People begin to visit multiple stores, increasing demand across a wider area. This spreads the shortage geographically. At the same time, delivery systems struggle to rebalance because transportation networks are already operating near maximum efficiency. There is no reserve capacity to absorb sudden spikes. What appears as a localized issue becomes a regional pattern. This is where the escalation begins. Certain states are structurally more vulnerable due to a combination of factors: heavy reliance on imported food, long supply chains, limited in-state production, high urban density, and constrained transportation corridors. States with large metropolitan populations but minimal agricultural output depend almost entirely on inbound logistics. If a major highway corridor is disrupted or fuel distribution becomes inconsistent, these areas experience supply delays almost immediately. In contrast, regions with distributed agriculture and shorter supply chains maintain partial resilience, even under stress. But the most overlooked factor is time compression. In previous decades, supply chains operated with buffer periods, extra inventory, slower turnover, and localized storage. Modern systems have eliminated these buffers in pursuit of efficiency. This means that disruptions propagate faster than ever before. A delay that once took a week to impact retail shelves now takes less than 2 days. This compression reduces the window for corrective action, leaving little room for intervention once the system begins to falter. As we move deeper into 2026, these vulnerabilities are no longer isolated. They are converging. Fuel price volatility affects transportation frequency. Labor shortages reduce warehouse throughput. Climate variability disrupts predictable supply patterns. Each of these factors alone is manageable. Together, they create compound stress on a system designed for stability, not resilience. And under compound stress, failure does not occur gradually. It accelerates. The states most at risk are not necessarily the ones with the least resources, but the ones with the highest dependency on continuous, uninterrupted flow. Places where a single missed delivery cycle can ripple across millions of consumers within hours. Understanding where these points exist requires looking beyond population size and examining infrastructure dependency, distribution density, and logistical redundancy, or the lack of it. Because once the first visible shortages appear, the system enters a feedback loop. Perception drives behavior, behavior drives demand, and demand overwhelms supply. At that point, recovery is no longer immediate. It becomes a process of stabilization, where restoring equilibrium takes significantly longer than losing it. And the critical question is not whether this will happen, but where it will happen first, and why those locations are structurally positioned at the edge of supply failure. The pattern becomes clearer when you map dependency instead of geography. The first states at risk are those where food does not originate, does not pause, and does not have time to recover if delayed. These are states where supply chains stretch thousands of kilometers, crossing multiple distribution nodes before reaching a shelf. In such systems, every additional step is a potential failure point. A truck delayed at a regional hub is not just late, it is subtracting inventory from dozens of stores simultaneously. When multiplied across hundreds of deliveries, the absence compounds faster than the system can correct. Consider the structural imbalance between consumption and storage. High-density states with massive urban populations operate on extremely tight inventory cycles. A single metropolitan area can consume thousands of tons of food per day, yet the physical storage capacity within city limits is minimal. Warehouses are often located far outside urban centers, relying on continuous transport corridors to maintain equilibrium. If those corridors are interrupted, by weather, fuel constraints, or infrastructure strain, the city effectively begins consuming its own reserves with no immediate replenishment. The clock starts ticking the moment inflow slows, not when it stops. A critical misunderstanding is the belief that alternate routes or backup suppliers can easily compensate. In reality, redundancy in modern supply chains is limited. Most distribution networks are optimized around cost efficiency, not resilience. This means that backup options are either slower, more expensive, or already operating at capacity. When primary routes fail, secondary routes cannot absorb the full load. The result is partial delivery, which is often worse than total failure because it creates uneven distribution. Some stores receive stock, others receive none, and consumers respond by migrating toward perceived availability, intensifying localized shortages. The hidden science behind this lies in network theory and flow optimization. Supply chains function as dynamic networks where nodes and edges represent storage points and transportation links. Under normal conditions, these networks operate near peak efficiency, with minimal slack. However, systems operating near peak efficiency are inherently fragile. Even a small disruption can push them beyond their threshold, causing disproportionate effects. This is known as a nonlinear response, where input and output are no longer proportional. A 10% reduction in delivery capacity can lead to a 50% reduction in shelf availability in certain nodes, depending on their position within the network. Empirical evidence from past disruptions reinforces this. During short-term crises, data consistently shows that states with high import reliance and limited internal production experience the fastest depletion rates. Coastal regions dependent on port imports face immediate vulnerability if port throughput declines. Inland urban centers reliant on long-haul trucking face similar risks if fuel distribution becomes inconsistent. In both cases, the system's dependency on continuous flow creates a narrow margin for error. Once that margin is exceeded, depletion accelerates. The survival implications extend beyond food itself. Grocery stores are not just food providers. They are distribution points for essential daily needs, including water, sanitation products, and basic medical supplies. When these items become scarce, the pressure on the system intensifies. People begin substituting, overpurchasing, or stockpiling alternatives, which further distorts demand signals. This creates a secondary wave of shortages that spreads beyond the initial disruption. The system is not collapsing, it is being overloaded by its own feedback loops. Escalation becomes unavoidable when multiple stressors align. For example, a fuel shortage does not just reduce transportation capacity. It also affects agricultural production, refrigeration, and processing facilities. Similarly, labor shortages in trucking or warehousing reduce throughput even if goods are available. Climate-related disruptions, such as extreme heat or flooding, can simultaneously affect production regions and transportation infrastructure. When these factors overlap, they create synchronized strain across multiple layers of the supply chain, leaving no single point capable of compensating for the others. Another overlooked factor is behavioral synchronization. In the digital age, information spreads instantly, and consumer reactions become highly coordinated. A single report of empty shelves in one location can trigger preemptive buying in another, even if no shortage exists there yet. This anticipatory behavior accelerates demand spikes, effectively pulling future consumption into the present. The system is forced to meet not just current demand, but projected fear-driven demand, which it is not designed to handle. States with limited logistical diversity are particularly vulnerable under these conditions. If a region relies heavily on a single distribution corridor or a small number of major suppliers, any disruption to those channels has an amplified effect. In contrast, regions with diversified supply inputs, multiple transport routes, varied sourcing regions, and localized production have more pathways to maintain flow. The difference is not just in capacity, but in flexibility. Flexibility determines how quickly a system can adapt when conditions change. As shortages begin to appear, the system enters a phase of visible instability. This is when empty shelves, delayed deliveries, and inconsistent availability become noticeable to the public. At this stage, recovery becomes more complex because restoring supply is no longer enough. The system must also correct distorted demand patterns. This requires time, coordination, and stable operating conditions, three factors that are often in short supply during a crisis. The transition from stability to instability is not marked by a single event, but by a threshold being crossed. Once crossed, the system behaves differently. It becomes reactive rather than predictive, struggling to keep up with rapidly changing conditions. Understanding which states are closest to this threshold requires examining not just their resources, but their dependencies, their infrastructure, and their capacity to absorb disruption without immediate failure. And as the pressure continues to build, the distinction between temporary shortage and systemic risk begins to blur, setting the stage for the next phase, where localized disruptions start to align into a broader pattern that is far more difficult to contain.